So today we're going to start in on chapter 4 and really start talking about antiderivatives. So, and a little bit about indefinite integration. So we can say a function capital F is an antiderivative of lowercase f on an interval I if capital F prime of x equals f of x, lowercase f of x. And if you think about what that's saying, the derivative of the antiderivative, excuse me, equals the function itself. So that kind of makes sense. Antiderivatives and derivatives undo each other, right? They're inverses, inverse operations. So if we had something like f of x equals x to the third, then we could come up with any number of antiderivatives for x to the third, just something whose derivative would become x to the third. So a basic one would be like, if I had x to the fourth, the derivative of that is 4x to the third. So if I divide it by 4, the derivative of this would be 4x to the third divided by 4, so that would simplify to x to the third. I could take that same term, x to the fourth divided by 4, and do something like add 5 to it. Because the derivative of the first term is still x to the third, and then the derivative of the constant term is 0. Anything, x to the fourth over 4, I could say minus 3. That again would give me the derivative of that antiderivative would give me x to the third. So in general, the general solution to the antiderivative of x to the third is x to the fourth divided by 4 plus any constant c. And so this c that we have is called the constant of integration. So you're going to be told over and over and over again, don't forget your plus c. The constant of integration is required on FRQ problems. So if you're doing an indefinite integration, and we'll talk about what that means in a minute, if you correctly find the x to the fourth plus 4, x to the fourth divided by 4, but forget the plus c, you'll lose at least 1 point on a 9-point problem. So just be careful. A reminder, a differential equation is the equation of the derivative, and the general solution will be the family of all antiderivatives. So differential equation was originally underlined here. We did differential equations. That's where you solve for dy dx and had both x and y variables in at least in your original equation. So that was the equation of the derivative, and general solution would be our family of all antiderivatives. So if I had to find the general solution of the differential equation dy dx equals 3, the general solution is basically just saying, figure out what does y equal. Y equals what? All right, so the y equals would be if I integrate, I know we haven't used the symbol yet, but if I integrate both sides, if I take the antiderivative of both sides, then I would get y equals the derivative of, or the antiderivative of 3 is 3x, because remember, you're thinking backwards. You're saying, what would I have to have taken the derivative of to get just plain 3? And then we have to have plus c, this constant of integration, because it could be 3x plus 2, it could be 3x minus 3/4, it could be anything with a constant term on the end. So the operation that I just wrote, that fun little like squiggly thing, what we're doing here is using indefinite integration, or that's also known as anti-differentiation. Because remember, we said derivatives are If a function has a derivative at a certain point, it's differentiable at that point. So now we're saying if we can take an integral, then we're doing antiderivative, so anti-differentiation. It's denoted by the integral symbol, which looks like this. All right, so here's what an antiderivative or an indefinite integral looks like. Y equals, here's my integration symbol. This f of x dx little expression here is called the integrand. And this little dx part, you have to have that. Again, if you write out an equation, you're taking the integral of an f of x, and you don't say, what is the variable of anti-differentiation? Like, what is this with respect to? Just like we have dy dx or dy dt or whatever, that denominator of that part tells you what you should be taking derivatives with respect to. It's the same thing here. What are we taking integrals with respect to? So this denotes the variable of integration. So you have to have a little dx on there. Sometimes it'll be du or dt. And then whatever that integral is equal to, it comes out as some equation. So capital F of x is our antiderivative, whatever that actual equation is. Antiderivative, we'll say, of f. And c, remember, is the constant of integration. All right. So we're labeling all these little parts. I think it can be kind of confusing as you're labeling everything, but once we get into some problems, hopefully some things might start to click. So, okay, here's a property that looks more complicated than it is, right? If I take the derivative, which is the dx part, of the integral of something, if I take the derivative of the antiderivative, then I get the function, f of x. If I take the derivative of the antiderivative of f of x, antiderivatives cancel out derivatives and vice versa, so I'm left with just f of x itself. And the opposite is true if you're starting out with the derivative of f, and that is supposed to be a lowercase f. So if you're starting out with the derivative of f of x and then taking the antiderivative of it, the antiderivative of the derivative should equal, again, the function itself, f of x. All right? Basically, all this is saying, this little star right here in the middle, this is just saying if you have time, you can check your work. Like, you can make sure that you got the right thing. If your goal was to find an antiderivative, you can always go back to your antiderivative equation, take the derivative of it, and make sure you get the original f of x. Or if you're starting with the derivative and then you take the integral of something, if you start with you get a derivative for your answer, you can always take the integral of it and make sure that you get back the original f of x. So kind of summarizing everything we have. If I say that I have an whoa, this is spelled wrong. Antiderivative of f of x, that is the same as saying I have the indefinite integral of f of x. Or if I don't write that out in words, it would look like this, the indefinite integral symbol of f of x with respect to x dx, f of x dx. Or if I actually get an equation for that integral, like I take the integral and come up with something, that's my capital f of x plus c. And then in general, what does the antiderivative represent? It is the general solution to the differential equation which is some dy dx equals some sort of f of x. You will be asked to find the general solution on some AP problems to a differential equation. So again, all that means is take the integral of dy dx and make it y equals something. So we're going to practice some kind of just some rules here and then work those into some properties. So start with the derivative, and then we'll go over to the integration. So derivatives are what we've been doing, right? This is like our chapter 2 stuff. And now antiderivatives are chapter 4. Okay, so the derivative of a constant is 0, right? That means that the integral, I want to kind of bullet point these so we don't get lost. The integral of 0 with respect to x, you still have to have the dx there, should equal some constant term. All right. The derivative of k times x is just k. So that means that the integral of k with respect to x is equal to kx plus c, right? The derivative, or the integral of the derivative, is equal to the original function itself plus the constant of integration. If we have a k in front of some function more complicated than just x, so it could even just be 2x or x squared or whatever, then that is equal to that constant k times the derivative of f of x, whatever that may be. And so if we go backwards and we have the integral of some constant k times whatever that derivative of f of x equation was with respect to x dx, then that's the same as, I want to write one extra integral here. You are allowed to pull the constant out in front of the integral, just like you can do with derivatives. Sometimes that makes things easier to look at, so I can pull the 2 or whatever it is out in front, take the integral, and then multiply it back into my answer. So my answer would be k times whatever f of x was, right, the original f of x, plus that constant of integration. If I'm taking the derivative of the sum or difference between two functions, that comes out to f prime of x plus or minus g prime of x. You can add or subtract those derivatives. And you can do the same thing with integrals. So if I have the integral of, I'm going to write like this, f of x plus g of x, plus or minus g of x with respect to x dx. You would need those brackets around that if you have two separate expressions in there. Then that can be split up into the integral of f of x dx plus the integral of g of x, plus or minus the integral of g of x dx. I don't have a plus c yet because I haven't actually taken the antiderivative. I haven't figured it out. I don't know what f of x and g of x are, so I can't really take it further than this because those aren't derivatives or anything. So just know that we're allowed to split up integrals just like we're allowed to split up derivatives. Basically, you can take the derivative or the integral of each term. Power rule for derivatives is to bring the n down, multiplied by x to the n minus 1. And so I'm not going to quite go backwards here, but it would work. If I take the integral of this, then, well, no, I don't want to work it backwards, sorry. So let's start here. The integral of x to the n. So I don't want to go with my answer from the previous one. I know the derivative, I know the power rule for the derivative. What if I have the integral of x to the n dx? Think about what we did with x to the third. When we had x to the third for our function, then when this was x to the third, then we got x to the fourth over 4. So it's going to come out every time to x to the n plus 1 divided by n plus 1 plus c. Because when you take the derivative of this, your n plus 1 comes out in front, cancels with that one. And then you have your new power is n plus 1 minus 1, which leaves you with n. So it does work. We do need to make a note here. N can't be equal to -1 because then you would get something divided by x to the 0 divided by 0 when you're actually doing that. So when you have x to the negative first power, or 1 over x, that is a different value, and we'll talk about that later. All right, we know the derivative of sine x is cosine x. So going backwards, I know that the integral of cosine x dx is equal to sine x plus c. And I know that the derivative of cosine x is negative sine x. So when I take the integral of, I'm going to be careful here. I'm not going to take the integral of negative sine x. I'm going to take the integral of sine x dx, because that's what it would typically be. The integral of sine x dx should come out to negative cosine x plus c. Right? Remember, you can check your work here. If I take the derivative of my answer, I should get the original integrand right there. So if I take the derivative of negative cosine, I get negative negative sine, so sine x, and the derivative of the constant is 0. So that does work. All right. The derivative of tangent x is secant squared x. So the integral of secant squared x dx is equal to tangent x plus c. The derivative of secant x is secant x tangent x, or tangent x secant x, whatever. So the integral of secant x tangent x dx, I don't need brackets around this because that's all multiplication, would equal secant x plus c. The derivative of cotangent x is, remember, if you know tangent, you know cotangent. It's just put a co in front of everything. It's cosecant squared x, negative. Almost forgot the negative. So if we're doing the integral of just cosecant squared x dx, so if it doesn't have the negative sign included, then my answer is going to equal negative cotangent x plus c. And finally, the derivative of cosecant x, again, if you know secant, you know cosecant, put cos in front of those. It's negative cosecant x cotangent x. So if we have the integral of positive cosecant x cotangent x dx, then that would equal negative cosecant x plus c. So when you're taking integrals, you cannot split apart integrals into a product or a quotient. So we do have, toward the end here, we have 3 integrals so far that involved, or 2, sorry, integrals that involved a product of 2 functions. But I didn't say this is the same as the integral of secant x times the integral of tangent x. I can't do that. But since secant tangent is the derivative of secant, that's how I can go ahead and take that integral. Okay? Same thing with squareds. You can't break cosecant squared x dx into like the integral of cosecant times the integral of cosecant, because you wouldn't get the same answer. If you did that, you'd have what? Like cosecant squared x, cotangent squared x or something as your answer, and that's not really going to work, or something like that. All right, so we are allowed to split up addition and subtraction. You can take the integral of each term, but multiplication or division, which we don't have examples of, but multiplication or division will not be split up into an integral times an integral. All right, so integrate each integral. Check your answer by differentiating. So the integral of 1 over x cubed dx, you might find it helpful to rewrite these just like we did with derivatives. And so I'm thinking of this power rule. Remember, the integration is add 1 to the exponent and divide by that new exponent. So when you add 1, you get x to the negative 2, divided by negative 2, and then plus c. Simplify, like we don't like negative exponents. So negative 1 over 2x squared plus c. And I'm going to check this first one, but I'm not going to do that every time. Check, remember, is just saying, hey, don't forget you can take the derivative of this and you should get back to the original answer. So the derivative of, going back to my pre-simplified term, the derivative would be -2 x to the -3 divided by -2 plus 0 for the constant. And yes, I do get x to the -3, which is what I was taking the integral of. So we're not going to check every single one of these, but if you happened to have extra time on a test, which we know is not typical, you could check in that way. Okay, part B, rewrite. Remember, you can take the integral of x to the 1/2 dx. All of these would get dx's though, plus the integral of x dx, plus we could bring the 2 out if we wanted to. I want to show it so you see what that looks like. I could rewrite in this way, and then that's equal to, let's actually integrate it. So adding 1 to 1/2 is 3/2. You have x to the 3/2. It's divided by 3/2. I'll simplify that in a minute. Plus 1 plus 1 is 2, so x squared over 2. Plus, remember, the integral of 2 of a constant is 2x. Even if I didn't have the 2 there, the integral of dx, that's like having a 1 there, is x. So I should have plus 2x and then plus c. And simplified, we don't want to have a complex fraction, so divided by 3 over 2 is the same as 2 times 2/3. So 2 x to the 3/2 divided by 3 plus x squared over 2 plus 2x plus c. The integral of 2 sine dx, remember you can bring the 2 out in front of the integral symbol. When you're showing your work, just like we couldn't drop limit notation earlier, you cannot drop the dx's in your work. Okay, so when I integrate, this is 2 times, what was the integral of sine x? So this might take some practice here before you get the hang of it. The integral of sine x was negative cosine x. Okay, so -2 cosine x plus c. And there's nothing to simplify for that. The integral of dx, they wouldn't show the 1 here, but this has been written in, I think, on your copy probably as well. So the integral of 1 dx is equal to x plus c. If you had to rewrite that, it is technically x to the 0. That's 1, right? Dx. So if you needed to rewrite to remind yourself, like, what is going on here if I don't have an actual variable, it is x to the 0. And then the power rule works. 0 plus 1 divided by 1 is x divided by 1. So, I mean, I'm hoping you can do it without having to do that every time, but as we're just beginning, that might be helpful. Now remember, for these last two, we are not allowed to say, oh, it's the integral of x plus 1 divided by the integral of square root of x. That does not work. So we need to rewrite this equation and simplify with what we do know. We can take the integral of different terms, and since this is a binomial divided by a monomial, I can go ahead and divide out. X divided by square root of x is the integral of x to the negative 1/2 plus the integral of 1 over square root of x. The integral of x to the positive 1/2, plus the integral of x to the negative 1/2, and I almost forgot to write dx for both of those. So I've gone ahead and divided each term by square root of x, and then I split that into the sum of two integrals. And then I'm just going to use power rule. So 1/2 plus 1 is 3/2. Remember, we had this before. X to the 3/2, instead of dividing by 3/2, I'm going to write times 2/3. And then negative 1/2 plus 1 is 1/2. So plus, it's going to be x to the 1/2 divided by 1/2, or times 2, plus c. All right, and on f, again, I can't say the integral of sine divided by the integral of cosine squared, but I can use my trig identities to work on this a little bit. This is sine x over cosine x, if that helps you. Sine over cosine is tangent, right? So I have the integral of tangent x 1 over cosine is secant x dx. Tangent secant should sound familiar. That's the derivative of secant, right? So the integral of tangent secant dx is equal to secant x plus c. All right, so I think that's it for our very beginning of chapter 4. Please come to office hours if you have any questions.